Eigenvalues are one of the most important numbers in mathematics. Why is that? There is a saying that, tell me about your friends and I will tell you about your future. Similar to that, if you know what the eigenvalues of a matrix are, you can tell a lot about the properties of the matrix, not just the given matrix. You can tell a lot about matrices that are related to the original matrix. For example, let's say P is any 3 by 3 simple non-singular matrix. Its eigenvalues are lambda 1, lambda 2, lambda 3 or 1, 2 and 3. Its first invariant known as a trace is the sum of the eigenvalues, which is 6. It's another invariant. Determinant is given by product of eigenvalues, which in this case is again 6. We can also tell a lot about what are the eigenvalues of related matrices like P transpose. We can also tell a lot about inverse of the given matrix, P inverse. How about we take the original matrix and keep on multiplying it n times, we get P power n. We can also tell the properties of this matrix. How about we take the original matrix and scale each of its elements by a constant k. We can also tell a lot about this matrix. How about we take the original matrix and add an identity matrix multiplied by a constant k. We can also tell a lot about this matrix. We are going to look at all those properties in this particular video. So the first question, what happens to the eigenvalues of P transpose, which is the transpose of the original matrix? Say the matrix is non-singular. Let's just look at a 3 by 3 matrix. The transpose is going to have eigenvalues as the original matrix, okay, lambda 1, lambda 2 and lambda 3. For example, if the eigenvalues of 1, 2, and 3 for the original matrix, eigenvalues for P transpose is going to be 1, 2 and 3. Accordingly, trace and determinant is going to be 6 and 6. Second, how about we consider the inverse of the original matrix? Inverse of the original matrix is going to be, the eigenvalues of the inverse of the original matrix is going to be 1 by lambda 1, 1 by lambda 2 and 1 by lambda 3. Essentially take the original eigenvalues 1 over the original eigenvalues. For example, if the original eigenvalues are 1, 2 and 3, in this case eigenvalues of P inverse is going to be 1, 1 by 2 and 1 by 3. Accordingly, the trace and determinants could be found from this. So this is going to be 1 plus 1 by 2 plus 1 by 3 and this is going to be 1 times 1 by 2 times 1 by 3, which is 1 by 6. How about P power n? That is, we take the original matrix, rise it by a factor of n. Again, we can say a lot about that. The original eigenvalues of lambda n, lambda 1, lambda 2, lambda 3, eigenvalues of this is going to be lambda 1 power n, lambda 2 power n and lambda 3 power n. There are m eigenvalues. Each of those eigenvalues will be raised to the power of n. For example, we take the original matrix, multiply it 3 times, okay. So the eigenvalues of this matrix are, so we have n is, let's say 3, it's going to be 1 power 3, 2 power 3 and 3 power 3. Accordingly, we will have the trace and determinants. How about take the original matrix, multiply it by a constant k. In that case, the eigenvalues are going to be, each of the eigenvalues are going to be scaled. That is, first eigenvalue is going to be k times lambda 1, second eigenvalue is going to be k times lambda 2, third eigenvalue is going to be k times lambda 3. For example, we take the original matrix, we scale each of its elements by a factor of 10, okay. Its eigenvalues are going to be 10 times 1, 10 times 2 and 10 times 3. Accordingly, the trace and determinant is going to be 60 and 6000. Okay, how about P plus Ki? We take the original matrix, add an identity matrix where the identity matrix is multiplied by k. In that case, the eigenvalues are going to be lambda 1 plus k, lambda 2 plus k, lambda 3 plus k. For example, if we add, say, 5 to the original matrix, okay, 5 times identity to the original matrix, the eigenvalues in this case are going to be 6, 7 and 8, which is 1 plus 5, 2 plus pi, 3 plus pi. Accordingly, we can find what the trace and determinants are. Notice, while having this discussion, we did not mention what are the elements of the matrix P. That's one of the powers of the eigenvalues. Just by knowing this, we know the major invariants. In fact, we know all the three invariants. The trace determinant, the second invariant is lambda 1, lambda 2 plus lambda 2, lambda 3 plus lambda 1, lambda 3. We also know that. In addition to that, we also know the eigenvalues and according to the invariance of all the related matrices, P transpose, P inverse, P power n, K times P and P plus Ki. Okay, I will conclude this video with some of the properties that emerge due to the result that I just wrote down. Okay, so we notice P and P transpose eigenvalues are the same. Okay, so if we take the look at the determinant of P, okay, that's going to be equal to the determinant of P transpose. Notice eigenvalues of P and P inverse are inverted. That is reflected in the determinants, right? 6 and 1 over 6. In fact, the determinant of original matrix P is going to be 1 over the determinant of P inverse. Finally, how about, not finally, we have a couple of more properties. How about P power n? Okay, so determinant of P power n, notice, so each of the eigenvalues is raised to the power of n, right? So we take lambda 1, lambda 2, lambda 3, the product raised to the power of n. So take the original determinant, original product lambda 1, lambda 2, lambda 3, raise it to the power of n. So we know the determinant of P power n. How about we take the matrix n K times P, multiplied by it a constant. So determinant of K times P is, you notice each of these eigenvalues has a factor of K. So lambda 1, lambda 2, lambda 3, the original determinant times K power 3. Okay. If there are n eigenvalues, in that case it's K power n times determinant of original matrix. And of course, we can also write down the determinant of P plus Ki, but it's not directly related to determinant of P. What can you say about the properties of a matrix given its eigenvalues? Please let us all know in the comment section. I'll see you with another video.